Bonsoir à tous et bienvenue à la Grande conférence de l'iREx de 2020. Hi everyone and welcome to the 2020 Grande conférence de l'iREx. My name is Natalie Willette and I'm the coordinator of the Institute for the Research on Exoplanets. The Institute is a world-class institute based out of the University of Montreal with members also at McGill University, Bishop's University, l'Université Laval, and recently the Planétarium Rio Tinto Alcan de Montréal. Our researchers, ranging from students to professors, are discovering new worlds and searching for life beyond the solar system. The study of exoplanets, or planets orbiting stars other than our sun beyond the solar system, is a booming field in astronomy, and the l'iREx is at the forefront of this cutting-edge research. We have a very, very strong mandate for education and public outreach, and we're national leaders in the communication of astronomy to the public. We organize and participate in a variety of activities and events, from science festivals to classroom visits to online videos for kids. So look at all of our interesting activities that you can find on our website. And also what we really enjoy doing every year is this Grande conférence de l'iREx. This allows us, using very generous donations from our donors, to invite a world-class researcher to come, typically in person, to Montreal and share their wonderful research with us. We're tonight on Facebook Live and on YouTube due to the ongoing pandemic, unfortunately. But a lot of our activities have gone online, and we can now access an even broader population. So hopefully there are people that are connecting in, joining us today from Montreal, Quebec, but also throughout all the provinces in Canada. So hi, everyone. If you haven't already, I encourage you to like and subscribe to all of our channels to stay in tune with everything that we're doing. And send us your questions and comments throughout tonight, because after our speaker gives her presentation, we'll be taking questions from the audience. If you can, try to keep the questions a little bit closer to the end of the talk so that they will be easier for us to access, so we can ask those wonderful questions to our speaker. We have two wonderful moderators with us tonight working behind the scenes. I wanted to give them a little shout out. So our outreach coordinator, Marie-Ève Naud, is working on our Facebook channel today, on our Facebook page. And Frédéric Baron, who is the outreach coordinator for the Observatoire du Mont Mégantic, is moderating the YouTube channel. So feel free to say hi to them if you can. As I mentioned, Clara, our speaker, will be answering your questions after her talk. So without further ado, it is my great pleasure to introduce our speaker for the evening, Dr. Clara Sousa-Silva, a quantum astrochemist. You heard that right. Sometimes I feel really fancy saying I'm an astrophysicist, but she is even fancier as a quantum astrochemist. Clara obtained her master's degree in physics at the University of Edinburgh and her PhD in molecular astrophysics at the University College London. She was then a postdoctoral researcher at MIT working on quantum astrochemistry, and she now holds a very prestigious 51 Pegasi B Fellowship at Harvard's Center for Astrophysics. So if you know a little bit about exoplanets, you'll know why the fellowship is named 51 Pegasi B. In addition to all of her wonderful research, Clara is also an avid science communicator and a strong proponent for STEM education. So feel free to ask her questions about that as well. She has founded and continues to lead several programs which allows high school students and undergraduate students to participate in real astronomy research. Clara has dedicated much of her scientific career to understanding molecules, but one has captured her attention in particular, phosphine. And tonight we're delighted to hear more about Clara's search for this odd little molecule and the places this research has taken her. So Clara, we're all very excited to have you here tonight, and we're looking forward to your talk.
Thank you so much for the introduction. I'm so pleased to be here, and welcome everyone. And bonsoir à tout le monde. I wish I could do this in French, but unfortunately my French is not good enough. But one day. But in the meantime, I'm really pleased to share with you my work. I made it quite short, so everyone has time to ask questions. But I'm happy to start sharing my slides now, please. So if people can't see my slides, do let me know. But otherwise, I'm going to keep going. So that introduction was all correct. I am a quantum astrochemist, and I am delighted to be speaking to you all today. So my professional goal, is to one day identify and understand an alien biosphere. And today I want to tell you how I'm trying to get there by studying all the possible biosignature gases that life could be creating, even the really weird ones like phosphine, and by training the next generation to join the cause. So how do we find an alien biosphere? Well, to answer that, let's reverse the problem. Could an alien civilization with their own astronomers and quantum astrochemists know that we have an inhabited planet? So imagine an alien astronomer on the other side of the galaxy looking for a habitable planet in her night sky. If this alien astronomer pointed their very powerful spectroscope at our sun, they would be able to split its sunlight into the sun's spectrum. And this is exactly what they would see. They would see that some of the light from the sun would have been absorbed by atoms and even molecules in the cooler regions of the sun where they can survive, and leave behind these tiny shadows or absorption lines. And that happens because molecules behave in a really unique way. Molecules still have to follow the laws of physics like we all do, but it's not quite the same physics as we are used to. Molecules are so small that their physics follow the rules of the quantum world. And one of those very special rules is that the molecules can only absorb quantized amounts of energy, and these correspond to specific wavelengths of the light spectrum and specific colors of the rainbow. Different stars have different atoms and molecules, and so they have different spectra, and this is our suns. So those alien astronomers could look at the spectrum and, using their universal knowledge of molecules that they would get from their quantum astrochemists, know exactly which molecules and atoms were causing these absorption lines and figure out the composition of the sun. And if they were patient and very fortuitously aligned, they would notice that every 12 years, new absorption lines would appear and then disappear, and then 12 years later appear again. And these lines would be due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun. And molecules within its atmosphere absorb new lines. So an alien civilization with only slightly better technology than we have now would be able to study these absorption lines and know that Jupiter has a huge atmosphere with not just hydrogen and helium, but also methane, ammonia, hydrogen sulfide, and many more gases. And if they were really careful, then every year a few much fainter shadows would appear and then disappear, and a year later appear again and then disappear. And these would be due to the molecules in the Earth's atmosphere also absorbing new lines of the sun spectrum, so that an alien civilization could study these absorptions and know that we are a thriving, complex, living planet by looking at the molecules that exist in our atmosphere. So you can think of our atmosphere and its subsequent spectrum as a planet-sized message communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute an awful lot. And these alien astrophysicists could do this for all the solar system planets and tell the difference between them by looking at the atmospheric spectrum of each planet. And if they did that, they would learn many things. They would learn, for example, that Venus is hell with very high levels of sulfuric acid. So any life that might be there would struggle, though we'll talk more about that later. And they would notice that Mars has a teensy tiny atmosphere that can barely shield its surface from the radiation from the sun, so also not the most hospitable destination. And they would know that out of the solar system planets, there's something really special about the Earth, and that is we have a lot of life, and we can and should do the same to them. Now, first, we have to find the planets themselves, and we've been doing that for a really long time. We found Uranus in 1781, Neptune in 1846. We found Pluto in 1930 and then lost it again in 2006. Then we found our first exoplanet in the mid-90s and kept finding more and more. With Kepler, we found thousands of planets, and with TESS, a recent mission, adding to the count, we have now detected over 4,000 planets. And with upcoming missions, we will find tens of thousands more. So we're getting really good at finding the planets themselves, but we have just begun finding atmospheres on these planets. And at this point, we still know very little about them. Future telescopes and missions will provide more data on more planets and their atmospheres, which means we are on the cusp of being technologically able to detect signs of life. When thinking about detecting life, how do we know what to look for? So we can start by looking for signs of life as we know it. The easiest biosignatures or markers for life that we can detect on exoplanets are beloved gases that we already know from our own life on modern Earth. And these that you see on your screen exist in our atmosphere in reasonable abundances. So molecules that life we find pleasant loves, such as methane, carbon dioxide, which are produced in large quantities by life, but even other molecules like hydrogen cyanide, which, although aren't particularly popular now as molecules that life produces, it was likely crucial as a building block of life. So it's a good pre-biosignature. So also interesting. So we know of these gases, and we can and should look for them on exoplanet atmospheres. And we can look for them by looking for these molecules' spectral signature. So each molecule also has a spectrum of its own, which looks roughly like these. And these spectra describe how each molecule interacts with light and where their absorption lines would fall on the spectrum of a sun's light. So if we want to detect any of these molecules on an alien atmosphere, we need to be able to either measure or calculate the spectra for each one of these molecules. Now, this is possible, but it is difficult, and it's often expensive, and it requires either a lot of lab work, often in dangerous conditions, and a lot of computational work, which is what I do, and that requires very, very large computers and many, many years of simulations for each molecule. But it's possible. But the thing is, even if we could detect all of these molecules on their own, these molecules would not necessarily indicate life, as they all have false positives for life, by which I mean non-biological sources that can also emit these molecules into an atmosphere. So things like volcanism, photochemistry. So you see here on the first column, these are all ways of making these molecules by life. But on the second column on the right, you'll see all of the other ways that these molecules can be made without interacting with life. And this is just a small sample. And this isn't some cruel astrobiological coincidence. This false positive problem happens because the chemical potential energy gradients that life likes to exploit are also easily exploited by geochemical processes. Basically, these molecules are lovely, but thermodynamically speaking, they're quite easy to make. And so life can make it, but not life can make it. Which means the detection of any of these molecules in isolation in an atmosphere wouldn't necessarily indicate life. Now, there are two solutions for this false positive problem. One is to carefully consider context. For example, oxygen on its own may not be a particularly good biosignature, but in the context of our planet, our sun, and the other components of our atmosphere, oxygen is a wonderful biosignature. But sadly, context is not always easy to determine. Knowing which molecules form the chemical and atmospheric context for a given biosignature gas is really challenging. In fact, my old group at MIT tried to be really agnostic and came up with a list of all the possible atmospheric gases that could form a biosphere. But that list contains 16,367 molecules. So the first problem is that this is a long list, but it is finite, so that's a start. But the second problem is that we currently only have the tools to detect a tiny fraction of these gases. And what this means is our ability to understand the chemical and atmospheric context of any biosignatures we might detect isn't great. And this makes it very difficult to resolve the false positive scenarios for those popular biosignatures of life as we know it. We can find them, but if we do, we won't be sure we found life. But life, as we know, is likely only one island in the vast archipelago of possibilities for life. Our galaxy alone has a huge diversity of stars, and orbiting them are planets of every kind. Earth alone has given rise to billions of different living species. So it isn't a big leap to think that life itself can arise in a huge array of unexpected forms, and that life would have many strange biosignatures beyond those that we are used to considering. Which brings me to the other solution to the false positive problem. We can start looking for the molecules that, although are less popular and maybe are associated with life that will be less familiar to us, are nonetheless biosignature gases with very low or no false positives, and so need less context to signify life. So a good example here would be CFCs, the pollutants, which can't really be made in any other way but life, though very irresponsible life. And so that's obviously an edge case with the CFCs. So I'll give you my favorite example that doesn't need us to be pollutants, and that is the phosphine molecule. Now, when I first met phosphine over a decade ago, it was very much considered a terrible biosignature, if a biosignature at all. In fact, at that point, phosphine was really only known for two things. One, phosphine was known as a marker for convection in Jupiter and Saturn. So phosphine is detected in the observable layers of these planets, but we shouldn't really expect to find it there. And that's because phosphine needs really high temperatures and very high hydrogen pressures to be thermodynamically viable. And that's not what happens at the very top of these planets where we see the phosphine. But what's happening is that phosphine is a scrappy and resourceful molecule. And so after being happily formed in the hellish depths of these planets, where it is thermodynamically favored, it resiliently makes its way to the top, surviving with several orders more magnitude concentrations that we would predict. So phosphine is really important for understanding the chemistry and the dynamics of gas giants, but it's much harder to sell it as a biosignature. And that's because the only other thing phosphine was known for was for being a horrific molecule. Phosphine is a highly flammable, extremely toxic, quite lethal, and outrageously foul-smelling gas. It's a really effective killer, which is why it's widely used as a fumigant on Earth, and sadly also why it was used as a chemical warfare agent in the First World War, and even more sadly, most recently by ISIS. It is also emitted to the Earth's atmosphere as an unfortunate byproduct of methamphetamine production. So I suppose initially I did consider it a biosignature of sorts, because if that alien astronomer detected it on Earth, they would know we like insecticides, war, and meth, which are all very unfortunate but unequivocal signs of life. So phosphine is awful, and most life avoids it, and I don't blame it. But as I was researching phosphine, I realized that for about 100 years now, there had been quiet but regular mentions of phosphine being found all over the place, which is really controversial because on rocky planets like the Earth, phosphine is so hard to make. It is so toxic to life and is so reactive with the radicals in the atmosphere that we really shouldn't see it anywhere. And yet we do. We find it in trace amounts ubiquitously throughout the globe and in weird places in strangely large quantities. So places such as sewage, marshlands, rice fields, lake sediments, the intestinal tract of fish, the intestinal tract of babies, the feces of penguins, the farts of badgers, and actually the intestines and excrements of most animals. And the one thing that all of these ecosystems have in common is that they are all anoxic. These are biological niches that are populated by anaerobic life that is not reliant on oxygen. And on Earth, these environments exist, though they are poorly studied. And here, phosphine is not so evil. It is only phosphine's relationship with oxygen metabolism that makes it so toxic. But for the majority of time that life existed on Earth, it didn't rely on oxygen. And so other planets with life less oxygen-loving than that on modern Earth could happily have phosphine as a popular biosignature. So, encouraged by this finding, we simulated many hypothetical spectra for many types of planets using many codes, all to figure out whether phosphine could A, survive in a variety of hypothetical planets with oxygen-poor atmospheres, B, whether we could detect it in the near future, and C, whether we could tell it apart from other atmospheric components. So I spent my entire PhD using quantum chemistry and very fancy supercomputers to calculate all of the spectroscopic properties of phosphine. And what I found was that it has a really distinctive spectrum that sets it apart from other molecules. But that doesn't mean it's easy to identify phosphine in the context of any atmosphere. For example, phosphine seen here in black, compared with other molecules you see in color, looks really easy to spot. But phosphine is not an easy molecule to make, so it's likely to be present only in quite small quantities in any given atmosphere. And this means its features can be easily drowned out by its atmospheric neighbors. Consequently, what I found was that only some scenarios would allow for the detection of phosphine-loving life. For example, if we consider observations with a near-future telescope JWST, which you see here on the corner, then for a hydrogen-rich or a carbon dioxide-rich super-Earth orbiting a cool small star, we could detect phosphine if it was created by life in at least these production rate values. Now, this may not mean anything to you, so I can compare it to the global rates of methane on Earth. And it is comparable to those. And it's also well below the maximum local phosphine production rates found on Earth above places like penguin colonies or sewage plants, where there's a lot of anaerobic life. Now, if we're looking at planets orbiting sun-like stars, phosphine is much harder to detect. In fact, only the puffy atmospheres of a hydrogen-rich super-Earth could let us see phosphine, and only if it was produced in comparable amounts to the highest recorded phosphine production rate on Earth. What this means is, to detect phosphine on an exoplanet orbiting a sun-like star, we would need a full sewage planet or an intestine planet, which I know doesn't sound particularly appealing, but I can assure you we would be disgusting to them too. Still, the takeaway is that phosphine is detectable and identifiable on some potentially habitable exoplanets. And to make phosphine even more appealing, it seems to have no significant false positives for life, as long as it's found on rocky planets, terrestrial planets, so definitely not a sign of life on Jupiter and Saturn. And we came to this conclusion by considering every false positive scenario we could conceive of. So first, we looked at the chemistry and thermodynamics of the formation of phosphine, and we found that in all cases, phosphine was highly thermodynamically disfavored. So then we thought, what if we introduced energy to a system? Could we force phosphine to be made, even if it usually wouldn't be made spontaneously? So for that, we looked at lightning and volcanism and meteors, and we found that even in highly reducing atmospheres, which should be the most favorable for phosphine creation, only a negligible amount of phosphorus could turn into phosphine, and always many orders of magnitude below anything we could detect. And at that point, we looked into increasingly more implausible scenarios, and none delivered any substantial false positives for phosphine. So we found that, given our current understanding of rocky planets and their atmosphere, we now had a tweetable conclusion, which you can see down here, that any detectable amounts of phosphine on a rocky planet could not be explained without life. Now, this paper was published in January this year, but it did spend a long time in revision. It was a large manuscript. And during that time, I told anyone who would listen about this tweetable conclusion, and I told many bored audiences that phosphine was a great, robust biosignature, effectively without false positives on habitable planets. And when I submitted this paper in 2018, I thought this was a cool conclusion, but it wasn't really controversial because it was just me describing a totally theoretical, hypothetical situation. I imagined a distant, exotic planet, not unlike the early Earth during the Carboniferous period, but without oxygen. So a wet, anoxic tropical paradise from pole to pole with a rich anaerobic biosphere producing tremendous amounts of phosphine. You might now know that this was a naive attitude, because a few months after I submitted this paper, I got a weird email from an astronomer from Cardiff, Jane Greaves, saying, "I think I found phosphine on Venus. Is that weird? I think it's weird." Now, I'm paraphrasing here. Jane is very professional. But Jane and her colleagues had a tentative detection of phosphine on the cloud decks of Venus, which is the only potentially habitable location on the planet. Now, Jane knew that might be a big deal, but she didn't know anyone who knew about phosphine in an astrobiological context. Fortunately, one of our mutual colleagues, Paul Rimmer, had been a member of one of those bored audiences where I told everyone about how cool phosphine is. So Jane got in touch to find out just how good a biosignature is phosphine. And I told Jane what I just told you, which is pretty good, like an extremely good biosignature. Are you sure you found phosphine on Venus? Because that's nuts. And that's how our collaboration began. For the next year and a half, we got more observations with ALMA, shown here in orange, that seemed to confirm the signal that we had got from the original observations with JCMT, shown here in white. And we worked really, really hard to figure out, A, is it really phosphine? And if it is phosphine, is there really no abiotic production mechanism, as I had claimed? So the observation team reduced the data and actually are currently re-reducing it. And they feel strongly that the signal is real, though weak. And at that point, we came up with a near infinite list of every molecular candidate that could plausibly and even implausibly be found on Venus. And what we found was that only phosphine was a plausible molecular candidate for the signal that we had detected on Venus. Now, that signal corresponded to a phosphine concentration of about parts per billion, which I know sounds like it's very little, but it's actually quite a lot of phosphine. So on Earth, for comparison, phosphine is only present in parts per trillion to parts per quadrillion. And at that point, led by William Baines, we redid and expanded the analysis that we did for my earlier paper on the possible formation pathways for phosphine on generic hypothetical terrestrial planets and applied it to the really concrete example of Venus, thinking, Venus is pretty extreme. Maybe there we could make phosphine. But we found that we could not, no matter how hard we tried, explain the presence of phosphine in the quantities that seem to be found in the clouds. So at that point, being faced with the exhaustion of all abiotic means of production, we seized on the possibility that this phosphine, if it is there, might in fact just be produced by life. Now, there's still much about Venus that we don't understand. So if you only take away one thing here is that we don't know Venus, and we really should. It's right there, shining brightly every night, waiting to be understood. But for now, with the data that we have and the knowledge that we have about Venus and phosphine, this is what we know. If the signal is real and it is indeed phosphine, all we really know is that something strange is happening on Venus. Some exotic, unknown chemistry. Whether it's exotic, unknown biochemistry, that's something for us to figure out together with the rest of the scientific community. But whatever the outcome, this is an extraordinary moment for astronomy and for my little molecule. So what happens now? Well, there are many next steps to understanding potential detection of phosphine on Venus, starting with addressing the primary uncertainties of the discovery, which are: 1, is the signal real for sure? 2, if it is real, is it unambiguously phosphine? And 3, if it is, what or who is making it? Now, several efforts have already begun to reanalyze the existing data and to see if there are any insights that we missed. Many groups are also looking at archival data, myself included, that we have from previous observations of Venus to see that if maybe phosphine was not found before because maybe no one was looking for it. But there are few existing data sets that can tell us about phosphine on Venus, and those that exist are noisy and delicate. So we also really need more observations that can not just confirm phosphine, but tell us about its temporal and spatial distribution. And then we also need new models that can simulate Venus and its atmosphere and its interaction with the surface and the sun's radiation so that we can better understand what is happening there. And all of these models and observations will fail if we don't have adequate fundamental data, like the spectra for not just phosphine, but all the other molecules that are around it. We have information about how the molecules interact with one another, with the radiation from the sun, with hazes in the clouds. And we can do this from laboratory work and theoretical work, but this will be vital to interpreting anything we see on Venus. And finally, unlike future potential observations on phosphine on exoplanets, in the case of Venus, we can actually go there and check. And putting aside any ethical issues we might want to have with potentially harming the first alien life that we find, it is worth noting that, again, data from any sampling mission will only be adequately interpreted if we have done our homework here on Earth by getting all this fundamental data ready. So lots of work to be done, but very important and exciting work. What I want to highlight here is how a virtually unknown and really quite revolting molecule became such an important piece of the puzzle in the search for life in the galaxy. And we can now look for phosphine on planets all over our galactic neighborhood. But we should remember the lesson here is not that we should look for phosphine, but that we shouldn't ignore molecules just because they aren't abundantly produced by life that we find pleasant and familiar to us. Whether you're looking for life by searching for these unusual biosignatures like phosphine, but many other weird molecules that I can talk about if you'd like, these weird, unusual biosignatures, which would only be present in atmospheres in small quantities, but have no significant false positives, or whether you're looking for the abundant potential signs of life, such as oxygen and methane, but need to consider less abundant molecules to resolve their false positive scenarios for life, the fact remains that we must be willing to consider more molecules, whether they're abundant or not. And do you remember those 16,367 molecules that life could be producing and releasing into an atmosphere? Well, out of those thousands of biosignatures, we have spectra for less than 4% of them. The remaining 96% are currently completely undetectable. Now, I do spend most of my time working really hard to solve this problem by simulating all of the missing spectra, but it took me half a decade to simulate phosphine. So I calculate it would take me well over 60,000 years to do this work by myself, which is something I realized about 6 years ago when I was nearing the end of my PhD. At the time, I was the head of education for the Twinkle Space mission, which is planned as a teeny UK satellite. But I was doing this while I was also training as a high school science teacher at a pretty rough North London school. We had no scientific resources, but yet whenever my research was mentioned in the classroom, the students and I would get into really interesting discussions, which made me think, what if I wasn't working on these molecules by myself? So I created a new program called Orbits, or Original Research by Young Twinkle Students, and recruited 15 of my own kids, my own students, to research molecules with me and 3 brave junior scientists who agreed to help. And this is them, the kids. The students were split into 3 groups, each dedicated to performing computational chemistry analysis on a molecule crucial for understanding alien planets. So I'd like to introduce to you Team Titanium Oxide, Team Acetylene, and Team Methane. Starting in 2016, these incredible kids learned astrophysics, quantum chemistry, programming, scientific writing, and performed original research on these 3 molecules. First, fearfully, but after a few months, you would have struggled to tell them apart from the young scientists I had brought into the school. So these kids went from being my high school students to being my official scientific collaborators. And to this day, we've published many scientific articles in peer-reviewed journals with the kids as co-authors and their school as an official institution right next to, MIT and Harvard. The students you see here, they became mentors for next year's students and those the year after and so on. Since 2018, where we've been collecting proper data, more than 100 school kids have become published authors of scientific papers. And we've seen the number of students that have taken advanced STEM classes have doubled in the schools that run the program. So small number statistics, of course, but I'm hoping we have had a positive impact on those communities. And to continue this work in the US, I became the director for the Harvard-MIT Science Research Mentoring Program. And in it, I recruit about 3 to 6 junior scientists and help them adapt their current astrophysics projects to benefit from the program. And I then hire 10 to 15 local high school students after a recruitment and interview process to participate in the program. And they get paid a yearly wage, $1,500, that is generously provided by a variety of lovely institutions. And I spend 1 month training all the students on how to be a scientist, how to perform astrophysics research, what is the imposter syndrome, how do you process astronomical images, what's an academic career. And this here on the right is us last year when we could work in person, assembling and using Galileoscopes at the roof of Harvard. Then the students all get grouped up with their mentors, and they meet with them for 2 hours twice a week for the whole year, and then present their work in an end-of-year symposium, which this year was completely virtual. Now, this has been a completely virtual program since March, and despite the difficult circumstances, if the last few years of the program are anything to go by, these kids will be publishing work and doing original research, and we expect major successes. I also run one other program called JURA, or Junior Research Award, which is aimed at students that have extraordinary potential but don't quite fit into a program like the ones I just mentioned, whether that because they're outside high school or their school is not quite in the right postcode for us to get funding for them. And this year's students for JURA are Kara and Asma, who've been working on the most accurate phosphine spectrum to date, and Emmeline, who's been working on cataloging planetary debris disks, and finally Megan, who's been working with me on characterizing pre-biosignatures, those building blocks of life. So this means it's not just me anymore. By training and supporting students, we're able to work on obtaining the molecular fingerprint, the spectra, for several new molecules, putting a small dent in that list of thousands of potential biosignatures that still need spectra. And ultimately, I believe that it won't be the next generation of telescopes that will revolutionize astrophysics, but the next generation of scientists. In the coming years, I want to do all that I can to give them the tools and aspirations to do exactly that. And when it comes to characterizing biosignatures, I calculate that if all the students I've trained join the effort, and I get that they may have other career plans, then we could get all that spectra done in much less than 60,000 years, in about 2 decades, which is really encouraging. But it also means that today, right now, we are not prepared to both detect and confirm the presence of most biosignatures on an alien planet that could be inhabited. So my current biggest professional concern is not that we will fail to detect a habitable planet in our lifetime. My biggest professional concern is that we'll point our fancy telescopes directly at an inhabited planet and just not have the tools to know it. But there are billions of stars in our galaxy alone, with billions of planets orbiting them. And these planets could contain trillions of life forms, releasing thousands of molecules into their atmospheres, just waiting to be detected. By using state-of-the-art computational chemistry and collaborating with students of all ages, I aim to provide the tools to understand alien biospheres so that one day we'll know life when we see it. Thank you.
Thank you so much for that, Clara. That was really great. And I am very happy that you had time to mention some of your educational programs. I'm always really glad that you highlight that. So several people submitted questions beforehand to enter our contest. And for those question askers, you'll be glad to know that we'll be doing a prize drawing, and a very lucky winner will be getting 2 books from one of your favorite people, Carl Sagan, whose birthday it was yesterday. So we'll be contacting the winner for that, for winning Cosmos and Contact. But we're also taking questions live, and soyez très libre de poser vos questions en français. Je vais pouvoir les traduire pour Clara au besoin. So we'll start off with some of the questions that we received beforehand, and I'll try to group some of them together because they sort of overlap each other. So, Danny Garot du canton de Hatley demande: est-ce que la forme de vie trouvée sur Vénus pourrait fournir de nouvelles explications sur les origines de la vie sur Terre? Et Nathan Baudouin de Québec demande: la vie sur Terre pourrait-elle provenir d'une source extraterrestre? So they're both asking essentially if this potential biosignature on Venus can give clues on the origins of life on Earth, and whether you think that the origins of life on Earth could be extraterrestrial.
So, multiple layers here. The origins of life could, on Earth, could technically be extraterrestrial. So this is called panspermia, which is a lovely expression. And although possible, I like to think of panspermia as kind of just passing the problem to someone else. It doesn't explain how life originates on Earth, but you then still have to explain how life originated wherever it came from. And so it's kind of just, we call that a displaced improbability. It's really hard to make life anywhere. We're going to have to explain it at some point if we want to do this work. And whether it originated here or there, we're still left with the same problem, which is explaining how it happened. Now on Venus, if there's life on Venus, we don't know what they're like and what they like. But we can guess that it's either very similar biochemistry to ours or very different biochemistry to ours. And if it is similar biochemistry to ours, then it probably could tell us a lot about how life happened and evolved on Earth. But it's also a really tragic possibility, because if they are anything like us, it will be an absolutely miserable existence. The clouds of Venus are potentially habitable, but they're still very hot and extremely acidic and crazy dry. There's no water there. And life on Earth, all the life that we know, loves water and hates acid. So it would not be having a nice time. But if it is totally different biochemistry from ours, it will teach us a lot about what kind of biochemistry can lead to life. So even if it doesn't tell us much about how life originated on Earth, it will tell us a lot about how life can originate anywhere. And that's worth it, I think.
Mm-hmm. Great. From Christopher Tail from Montreal, he asked, what new technologies or improvements to existing ones were needed in order to make this discovery?
Great question. So we have ever more powerful telescopes, but often we are trying to just collect every tiny photon from a really distant light source to try and understand what's on it. With Venus, we kind of have the opposite problem, where Venus is so bright that we actually don't have that many fancy telescopes that can study it very well. And to be honest, we kind of lost interest in Venus in recent years. We used to really care about Venus, and we sent lots of things there, but they all melted rather dramatically on the way down. And so we stopped. We didn't feel very welcome in Venus, and we started focusing on more docile planets like Mars, which may not be inhabited, but at least they don't like melt you on anything. So we need specific telescopes that can handle the sort of brightness, the specific properties of Venus. And then when it comes to finding phosphine, no one was really looking for phosphine. As I mentioned in my talk, it wasn't really in anyone's mind. I stumbled on phosphine during my PhD, but the whole decade I've been working on it and telling everyone about it, no one really has cared. So I don't think anyone was looking for phosphine. So that was less of a technological obstacle and just lack of interest.
Mm-hmm. Like a mental barrier to try to get people interested.
I mean, it's disgusting. Of course we weren't focusing on it. It's just awful.
That's a good segue to something that I've been wanting to ask you for all the entire time that we've known each other, and you talking about phosphine. You talk about phosphine in such a way that it sounds really horrible. And so in my mind, I'm imagining something that smells like rotten eggs, like sulfur. But what does phosphine smell like?
So in absolute technical terms, phosphine actually has very little smell, though we don't entirely know it because those who have smelt it have not lived to tell the tale. But it's almost impossible to make phosphine without making phosphine, so the rest of the family, and the family stinks. So it's supposed to be kind of like fishy eggs of garlicky death. There's one technical report that describes it, and this is a technical report, I need to find that citation, that describes it as smelling like the rancid diapers of the spawn of Satan.
Wow.
Beautiful. It's poetry, really.
Okay. All right. So if there are life forms on Venus, they don't have our same kind of preference for smells.
No, I mean, they probably think we stink. You know,
that's right.
What we find good smells are things that are good to us and are poisonous to us, and they're likely to think the same. And oxygen-loving life is probably extremely poisonous. It's definitely extremely poisonous to anoxic life. And so we smell terrible to them. This is all a problem for, galactic diplomacy to overcome.
So we'll take a question now from our live audience. So and this is great because this also covers the question from Jean-François Gélina from Montreal, who asked, should we only look for signs of life as we know it on Earth, or are other possibilities assessed? So Mirko is asking, what definition of a living thing do you use to look for life, to determine if there is life on a planet somewhere?
So kind of two sides to this. I specifically try to avoid looking for life that we find pleasant, the life that is common, but obviously I'm human and love oxygen, and so I'm for sure biased, but I am trying to be agnostic when I look for life. And phosphine is kind of the first step in that investigation, where it is definitely produced by life on Earth, but it's not really the life that we usually think about when we're looking for aliens. And to avoid more kind of Earth centrism, the other thing I try to think is not about a very strict definition of life, because even origins of life people argue all the time about what is the definition of life. But one of the few things that they don't disagree about is that life is likely to metabolize. So we don't know what life will be, but we know what life must do. And that is take stuff from its environment, do stuff with it, and then release other stuff. It's never going to be 100% efficient system that just takes things in and never gives back. And so this giving back, these metabolites, will definitely happen, and will definitely have to be made out of elements from the periodic table. We all have to follow the same rules of physics and chemistry in the universe. And so that's how I avoid that Earth centrism and that definition of life problem. I just look for the signs that life didn't mean to make.
That's great. And it's a question we get a lot, and it's a very complicated question. Yeah. But often we end up using definitions as we know them on Earth because it makes it a little bit easier. It constrains.
Yeah, you can say evolution or reproduction, but all of these are contested. And so I just focus on the basics, which is must, fart.
All right, great. That's a very tweetable answer.
Oh, please don't. Please.
Okay.
Please don't. Dr. Sousa-Silva, alien project.
Okay, all right. A question from Alexandra Lissouba from Montreal. Est-ce que le taux de phosphine dans l'atmosphère peut varier de manière saisonnière sur des mois ou des années en fonction des saisons sur Vénus? So they're asking, can the rate of phosphine or the quantity of phosphine that you detect change seasonally depending on the seasons on Venus? Maybe you can talk a little bit about the seasons on Venus, what they're like.
So we do expect seasonality to affect any molecule that's being produced by life. Certainly on Earth, that's what happens. And one of the plans when we are doing follow-up observations to try to unambiguously confirm phosphine is to also map it. So we see where it is and how it varies throughout the year. So definitely part of what we expect. But about the variation that we expect in the clouds, that's something that we still know very little about. Certainly in the two observations that we made that were 18 months apart, the abundance was similar, but we were also probing reasonably similar places in the clouds. And I think I saw at some point in the questions, there was another question mentioning, the recent observation and recent analysis of archival data that I was also involved in, but only very tangentially, that found an upper bound of phosphine. So couldn't really see the high abundances of phosphine we would hope, using a different wavelength region, and more importantly, probing a different altitude. And so we still don't know exactly what the variation in time and in latitude and in altitude that phosphine has. But if it is produced by life, big if, of course, we do expect it to vary the same way molecules produced by life on Earth change with those factors.
Yeah, one thing that I found really interesting in the paper was that when you were looking at altitude away from the equator, at some point you did stop seeing the phosphine, and it corresponded really well to convection cells that you were previously identified in Venus. So there is some correlation. Whatever is going on there is sort of like trapped within that cell. So,
I know, which is so cool. And of course, if it is a biosphere, big if, of course, that makes sense that we would get more in the mid-latitude regions, less in the equator, and very little in the poles. So all of these are, tiny little pieces of evidence for something cool to be happening on Venus. And now we just have to figure out what.
Mm-hmm. So we're going into something that's maybe a little bit easier or maybe very hard, depending on what you think. Vincent Filion from Baie-Saint-Paul demande, quel objet céleste préférez-vous observer? So we know your favorite molecule is phosphine. What is your favorite celestial object?
Oh, that's easy. It's the Earth. It's the Earth. Of course. It's the only habitable place for me and you. It has seasons and rain and oceans and forests. So far, everything we know about places out there is that they're less fun than this one. That's what we have. Maybe one day we'll find a celestial body that I can prefer, but so far it's Earth. Easy.
That's a wonderful answer that I don't think I've ever heard from an astronomer before.
Yeah, let's not ruin this one. It's my favorite.
We'll take a question from the live audience now. Ed Hudson, great talk. You talk about the need to calculate spectra for all these over 16,000 molecules. Any help from existing experimental infrared spectra?
Yes, so out of those 16,367, we do have almost, I think we have 600 of them. So we're only missing 15,744.
Only that's...
yeah. Easy. So those 600, a lot of them are in the infrared. They've been measured in the lab, but often they were measured, 30 years ago by someone who scribbled the spectra on a paper and then died years later. And we have no way of knowing what the uncertainties were, what the baseline was, what the instrumental properties were. And so a lot of these 600 spectra that we have, they're very poor and would be just about a little better than useless at using them to detect these molecules in space. But I'm counting. Any spectral data I get and I find, I put it into my database and I use it to inform calculations of future spectra, future molecules in different temperatures and pressures. But yes, I'm not throwing anything out. Any existing spectra I take and I use.
Great. So we have Germain Talbot from Lévis who asked, est-ce que la phosphine a été découverte sur d'autres planètes ou encore exoplanètes? Or has phosphine been detected on another planet than Venus or exoplanet? And you mentioned a little bit about the gas giants, Jupiter and Saturn. But how about exoplanets?
So far, nothing. I would have been very excited about that. Jupiter and Saturn, of course, we know why it's happening because there are places where it can be made. And by analogy, we also expect cool stars to be able, and circumstellar disks to also be able to make them. And in those sorts of places, we have found phosphine in a few locations. But even in other bodies of the solar system, like Uranus and Neptune, we haven't found phosphine. And so we have not found phosphine in a lot of places. We have found phosphine in very few places. And every place we have found phosphine, it either has access to some extreme environment that can make it, like Jupiter, Saturn, or a circumstellar disk, or on Earth, it was made by life exclusively, as far as we can tell. So that's why Venus is such a strange consideration.
Yeah, and you weren't even looking for it.
No, I mean, Jane was.
You weren't.
I wasn't looking at the solar system, but Jane was, and she had a kind of a long list of possible biomarkers, and phosphine was one of them. So I'm really pleased that Jane, dared to look at Venus, but it really just wasn't something people were looking for. So far, very few places have had phosphine.
Mm-hmm. Rosemary Williams from Pierrefonds asks, which life experience have driven you towards STEM fields?
Hard to know. My parents were both kind of really excited to show me science things. I spent a lot of time in the Palais de Découverte in Paris. My parents took me there multiple times because there were lots of cool things for me to touch. Sorry for the terrible accent in French. I was very little when I went. And so I spent a lot of time going to these museums with my parents and, poking things and pressing buttons. And I do remember when I decided to be an astronomer. I was 12 and I watched a solar eclipse, and my mom told me the exact timings that everything was going to happen at. And my mom was so bad with time. She was late for everything. She never knew the time. She didn't own a watch. And so I was just really confused that my mom was telling me with exact timings how things that were going to happen in the skies that she could not possibly know. And then it did. It happened exactly as she said. And I just thought my mom was the coolest ever. And when she explained she got all this information from astronomers who get paid to know the heavens, that was me. I was sold. And from age 12, in that moment, I decided one day I was going to get paid to know the sky.
That's so great. We'll take a question from our live audience now. Kareem Jaffer asks, have you brought aspects of your projects into the Citizen Science Forum to enlist amateur enthusiasts as well as students? You do have a lot of molecules to go through.
Yes, I would love to. But that, engaging a large-scale citizen science community takes kind of a platform that can work. So something online or some easy software where I can put all the work that I do on supercomputers and I do with the kids by bringing them to MIT and Harvard online. And I would love to. I mean, if the citizen science community would be willing and happy to participate in this, maybe it wouldn't take us 20 years, never mind 60,000 years. So I would love to. I just don't have the resources in terms of money and time. And I also don't have the programming skills to create this platform. But if anyone here is interested in doing this, I would be so thankful because that's something I haven't done and I would like to very much.
I don't know what the Zooniverse process is. Zooniverse is a really great platform with lots of different citizen science projects. For those of you who don't know, it's zooniverse.org, where you can be a planet hunter and find planets or classify galaxies by their morphology. So yeah, I have no idea how easy it is to plug into that community, but something to explore potentially.
Yeah, I would love to if I can.
When in your ample free time, when you have nothing to do, of course. A question from Jessica Williams Daly, also from Pierrefonds. How do you intend on making science a more inclusive world, particularly for girls who are interested in the STEM field? So when I always wanted to be an astronomer, so I just kind of worked towards that. But as I actually made it through, I finished my undergrad, I did my master's, my PhD. Every time I went up, the demographics got narrower and narrower. And I had a wonderful boss, but, he was still an old, straight white man who was lovely. And everyone above me just looked like him. And
he was extremely dedicated to trying to create a more inclusive team. And so he had very good hiring practices, and his head was really in the right place. And I thought, oh, great, maybe we can change things. But then our applicant pool was all like him again. And that was so depressing. And it was only then that I started really looking into it and found this kind of leaky pipeline where underrepresented minorities and girls specifically just disappear from STEM fields much earlier, not just in undergrad, but at high school. And so that was actually why towards the end of my PhD, I became a bit kind of disenchanted with the demographics of academia and started training as a high school teacher to try to kind of actively improve the pipeline. I think that was the right thing to do, but being a teacher is so hard. So hard. I mean,
thankless a lot of the time.
Oh God, it's thankless. It pays poorly. Your heart and soul. It's the most intellectual, psychological, physically demanding job I've ever done. People think rocket science is hard. They have no idea how hard it is to teach middle school science. It is so much harder than astrophysics at MIT. Like so much harder. I've done both. I know. And so I quit and went to MIT, where it's much easier. My job is much easier now than when I was a teacher. And so I think I know the solution. The solution is to bring science to the kids, let them actually do it. Most of the outreach projects that I witnessed, it's just very cool scientists coming to schools, telling the kids about the cool science that they do. And most of my efforts are all about going to schools or getting kids to come over and have them do the science. And I think that really makes a difference, at least in the numbers we're seeing now. So I'm hoping the next generation will look better than mine.
I think it is going in the right direction, but it takes effort from people like us and like you making that change. So,
but thank you to all the teachers who stay in the profession. You are all saints, even the bad teachers. You're still saints. Yeah.
Corinne Roy from Brownsburg, Chatham asks, aimerais-tu aller sur Vénus, or would you like to go to Venus and perhaps space in general?
So no, actually, I obviously would be cool to go once. I'm not immune to the idea of seeing Earth from the outside. But I think that all the telescopes, all the missions that have people go places are extremely expensive, quite dangerous as well. And for the amount of money that we put into these missions, we could fund dozens of PhD students, dozens of outreach programs to get young kids into science. We could really expand the field, and we could do, for example, all of this data that we're missing on Earth, and do it here and fund science that is applicable not just to future missions, but observations from Earth. So it's not that I'm against these missions, and of course I would love to go on a spaceship. I'm not, I'm not insane.
You are an astronomer.
Yeah, of course I would. But I actually think our priority should be on Earth and this sort of like thankless job, thankless work of doing reference data and really good fundamental science that we often dismiss.
So we're closing out on 1 hour. We're going to take one last question from the live audience. No pressure. Make it a good one. Lily asks, it says, amazing talk. What advice would you give to someone wanting to pursue a career in astronomy, astrophysics?
So I can't speak for everyone, but what I can say is I didn't have the best grades. I didn't have straight A's or anything. I was pretty okay at school, but I got just, a lot of B's, and I often didn't work particularly hard. And, when I got to university, I failed a bunch of exams. And I'm still a pretty good quantum astrochemist. I'm pretty good at studying space. And so my best advice would be, if you like it, don't worry whether you'd be good at it. Try. You probably don't need to have the sort of grades that you think people do. And then my other piece of advice would be to not worry about a specific career, particularly for something like astrobiology, the work that I really enjoy doing. We needed people who know instruments, like engineering people who understand optics, people who understand atmospheres, people who understand biochemistry, people who understand geology, people who understand quantum chemistry. And so the team had to be large. And that was really cool to do a large collaborative international collaboration. What this means is you can come at it from many directions. So just find the science you enjoy doing in school. Don't worry about your grades too much and keep at it.
It's great advice, and I would mirror that advice as well. So that's our time for tonight. Unfortunately, if I didn't ask your question and you sent it beforehand, either it's because it was answered throughout Clara's talk, or we didn't have time, unfortunately, but you're going to all be submitted to the drawing for the prize. And if you asked a question on Facebook, we will do our best to try to answer them in writing afterwards. So I'd like to thank Marie-Ève and Fred for all their help in organizing and managing this event with me. And a huge thank you to Clara for taking the time to communicate your research, but in particular, your enthusiasm and your passion. So thank you for sharing that with our community, and also for the time that you took yesterday to talk to our smaller group. We'll be staying tuned and hoping to see more developments on all of your research. And hopefully you'll be able to come to Montreal in person next time instead of only virtually. A big thank you to our generous donors, including the Trottier Family Foundation, without whom none of our activities, both scientific and educational, could happen. And finally, a big thank you to everyone that's listening tonight or at any other time, because this video will be available to rewatch on our Facebook and our YouTube. So if you like what you saw tonight, again, I encourage you to like and to follow us so you can learn about all of our upcoming events. And that's it for us. So thank you all again. Merci à tous. Have a wonderful evening. Take care of yourselves. Prenez soin de vous. Bonne nuit.
Merci à tous.